All right, good afternoon, everyone, and good morning if you're reaching us from the West Coast or somewhere else. I know we always have some great attendance from all over the world at these things. I'm Dave Broadbent, ABYC's Education Director. Look a little different these days. Still haven't gotten a haircut from COVID, so I hope everyone out there is staying safe and well. The other guy on the screen is Don Wilson with Xantrex. He'll introduce himself a little bit after I go through a little bit here. But we're really excited to have him here. He's going to go over a great topic on how to build a more efficient electrical systems with some of the new technology out there. So I think you'll all learn a lot. We'll have some time for some question and answer at the end, as always. So just a couple updates. Since last time we talked, we did release Supplement 60. So that has some great new standards in it. It has a new lithium ion tech info report. So take a look at that if you haven't. Here we are, fall webinars again. I think we're on number 12 now. And we have our schedule built out, which I'll go over in a little bit. We do have some sponsorship opportunities available. So if you're interested, I have Shannon's email address there. So give her a shout if you're interested in sponsoring any of these. Registration, as always, we offer it to members first. And if there's any other topics you'd like to see in the future, please let me know. CEUs, just to refresh everybody, or if it's your first time watching one of these, if you want to get your continuing education unit, there will be a follow-up email that comes out tomorrow. You can click on that link. It'll take you there to apply for them, and you're good. And if you're watching this on YouTube, at the end of the video, a little link will pop up for you to click to apply for your CEU. So any issues with that, you can email education@abycinc.org. Questions for the end, we're going to hold them all as we always do till Don's done with the presentation. There's that little question box, so type any questions you have there. We'll try to get it to as many of them as we can within that time frame here. Interactive online courses, we scheduled them out through 2021 now, April 2021. So take a look if there's anything you'd like to see. We've had some great success with our online classes. Yeah, we should have our advanced electrical working on that one, getting something up for that. So we pretty much, I think, have them all covered right now. So take a look at the schedule. If you're interested, register for a course there. And the next webinar is going to be October 15th, followed by November 5th, November 19th, December 10th, and January 28th. So mark your calendars. We have some great topics with Xantrex topping us off here, or starting us off rather. We'll do a bow thruster install, go through a little bit of that, some fire, electric propulsion issues. So we got some great stuff coming up. So I got through all my boring stuff here. So I'm going to go ahead and turn control over to Don, and he can introduce himself and teach, learn. We can all learn something today. All right, I'm turning over control to you, Don. I'm going to drop off my camera. We should be good to go.
All right, we are good to go. Hi, I'm really happy to be here. I appreciate this opportunity to do some training. I tell people all the time, one of my favorite things about my job is to train, to get in front of a group of people and talk about the things I know and kind of share some of that. We're going to talk today about emerging technologies, specifically as it relates to solar and lithium, from the perspective of an applications engineer rather than a design engineer, and what I deal with out in the field and a lot of the questions that I get asked. So just to introduce myself, I'm an applications engineer for Xantrex. I'm also the author of the Tech Doctor program that we've done. It's print articles and some YouTube videos that follow two rules. The first rule is we cover the technical subjects without talking technical, and we don't push product. It's not marketing, it's just flat training. So let's go ahead and get started. I think I'm where I need to be. Okay, so most of the marine market is fairly comfortable with inverters, and that's certainly where we kind of started our road into the marine market. There haven't really been a lot of advances that have been made there in the last few years. There's a few with NEMA 2000, things like that. But I get a lot of questions about solar and batteries. So we're going to focus on that today. In fact, let me go ahead and turn off so you can see my screen. There we go. So most of the content I'm going to cover today relates to our Freedom eGen technologies that we put together a few years ago to kind of combat the weaknesses in most generators that are out there. Its main focus is to either eliminate the generator or use the generator less and for its most effective purpose, and that's to be fully loaded through the entire run cycle. And that the biggest benefit to that is lithium technology and solar. So maybe, there we go. When I help design systems, the main categories that go on the drawing board are these four that you see here: energy creation, energy storage, energy conversion, and then energy usage. So when we look at energy creation, where's the electrical energy coming from? Is it solar, shore power generator, or even the engines? Energy storage, when we create an excess of energy, how can we best store that for the times when we have an energy creation deficit? And then third, the energy conversion, how best to convert that energy from AC to DC or DC to AC. And then energy usage. And this is kind of the holy grail, because that's what we're trying to do. We're trying to use the energy that we're storing. That's what the creation, storage, and conversion is all about. How are we going to use it? And we're going to get to know our little margarita maker here fairly well. So we're going to start with the steps that I go through to size a solar system. The 4 steps we take in solar is know your consumption, know your supply, identify the potential gaps, and then assume performance. And we'll get into that assume performance, because that's going to be key. First, the know your consumption. My advice to always calculate your usage to watts, since that's the universal, regardless of whether you're pulling from DC directly or converting to AC. Wattage is calculated by multiplying the voltage feed into the load and the amperage pulled by that load, but most devices have their wattage rating printed right on the case. So let's look at our blender. This is our blender. We need our blender. This is an important part of our experience. So what's the wattage of the blender? Well, if we look at the case of the blender, we can see that its draw is 750 watts. So that's our load that we're going to be trying to feed. The next thing we need to do is calculate how many hours we're going to be using our blender to make our margaritas. So let's say we typically make 3 drinks. It takes about 5 minutes for each one. And so when you calculate that, it's 3 times 5, 15 minutes, or a quarter of an hour at 750 watts. That calculates out to about 560 watt hours. So that's how much energy we need to get. But what about Friday? So Friday, we live life a little differently. We're going to make a few more drinks, so we really want to calculate the worst case scenario. On those days, let's say we're going to do 18 drinks. Now, they're for friends, I promise. But this calculates out to about an hour and a half of running time at that 750 watt load, or about 1125 amp hours, or excuse me, watt hours. Remember, we still need the system to feed my demand, even on the heaviest demand days. Okay, so always calculate to worst case scenario. The next thing we need to do is we need to consider the losses and allow for that. What I mean by that is if we're talking about drawing from solar, that's going to create DC power. And then the inverter converts that to AC, but the inverter is about 90% efficient. So we need to add about 10% of our demand, or add 10% to our demand to cover those losses. So that calculates out to about 1,237 watts. So let's take that number and put it aside. Let's talk about solar. How can we get 1,237 watts? So in our example, let's take our 300 watt panels. That's going to give us 300 watts anytime the sun is shining, right? Well, not really. So let's kind of look at the dirty little secret about solar panels, and that is that solar panels work best when the sun is perpendicular to the panel. That's where the panel will draw more energy from the sun. However, at some steeper angles, you'll get less energy into the panel. And so this kind of concept is covered by a term called insolation. Insolation is defined as the amount of solar radiation reaching a given area. There are insolation maps all over the internet. Here's one that I kind of picked out. And you can see that if we've got our sailboat on the hook just off the coast of Oklahoma City, which is, well, okay, let's say Miami. Miami has 4.5 insolation hours, or 4.5 solar hours in a typical day. Okay, So what that means is we can take that 300 watts and multiply that by 4.5 to get our total. But there's more to be considered in that too. It's not just how many insolation hours you can get in a day. Temperature comes into play too. Solar panels are designed or rated at about 77 degrees Fahrenheit. And so this is where they get their wattage rating. But if the solar panels get hotter, they put out less energy. So you need to consider that temperature coefficient. They're all different. They're all in the data sheets, and you can do some playing around with that to size your system. But for this conversation, let's assume it's always 77 degrees in Miami all the time. Let's take our 300 watts, multiply that by our insolation hours, 4.5 hours. That should give us 1,350 watt hours of draw from the solar panels during a typical day. So does that work? Well, our little margarita maker says yes. We'll get 350 and we'll use 1,237 on a Friday, so we're good to go there. Now, what about the next step? The next is identify the potential gaps. What I mean by that is when solar can't perform well. We've talked about insolation days, but those are typical days. So what are the things that can get in the way of solar performing? First is cloudy days. You can't generate as much energy when the clouds are covering the sun, or shadows covering the sun, or if the solar panels get hot, or if they're dirty. So a couple of these things we can take care of. We can keep our solar panels clean, so that's a little bit of maintenance we've got to do. We can try to stay away from shadows, but the weather we can't really do a lot about. So there's some things that we can control and things that we can't control. Okay. So what do we do in the meantime? Well, that's where batteries come in. This is where we really need to size the battery to make sure the battery is sized not only to get us through the night, but to cover the days as well where we're having harvest issues. Okay, so always make sure you've got enough battery to fill in the gaps in your solar performance. Okay, and on the topic of performance, assume performance. What I mean by assume performance is assume poor performance. Not that the batteries are going to perform poorly or the solar panels are going to perform poorly, but there are things that are outside of your control that might give you some bad days. So my general rule is always overestimate, always. And here's why. Here's a tracking for 7 days during a week. And on day 1 and 2, we're keeping up with our usage fairly well. 3 and 4, we've got an excess, which is great. But day 5 comes around and it's a cloudy day and we've lost all of our gains. And so on day 6 and 7, we're doing all right again. But in those 7 days, we've got one day that it didn't work. You've got to be a little bit realistic in how this covers, because if your system works 95% of the time, great. What about that other 5%? So you've got to have alternative strategies to cover that. So if you think you're close to your usage, you've done the calculations, you're close to your usage, add that little bit extra to make sure. Okay, so again, to wrap up the solar part, know your consumption, know your supply, identify the potential gaps, and then assume it's not going to work as perfectly as you calculated. So let's look at a typical energy system and talk about some of the things that can be offered to run that system. So there's our little margarita maker again. We make a full line of products that kind of go from beginning to end. And until we start making blenders, I got to say almost beginning to end. So let's cover the typical off-grid system. You're going to take your solar power. The solar panels have to go through some kind of solar controller. We'll get to that in a second. The solar controller then feeds the battery. The battery feeds the DC appliances directly or through an inverter to the AC appliances. But let's start from the end and work our way backwards. So let's look at the inverter first. all kinds of different types of inverters on the market. What we're looking at here are the three kind of categories that I put them in. First is the inverter, the standalone inverter, which is basically an inverter with a transfer switch. When there's not external power like a generator or shore power, the inverter feeds the blender. When you plug in, the inverter will see that incoming power, transfer it through to the load, and power the load by bypassing the inverter. And the inverter kind of goes into this standby mode, just waiting for you to unplug or to turn off the generator, and then it'll take over the loads. The second category is the inverter charger, like our Freedom XC. It works the same way as the standalone inverter. It has the transfer switch. It'll take power, it'll pass it through, and when there's no external power, it will invert the downstream. But when there is external power, it not only passes that power through, but it'll take part of that power and run an internal battery charger and charge the batteries. And so everything's kind of in one case. I tend to advocate for the inverter charger over the separate inverters and chargers for a couple of reasons. First, there are certain benefits you get with a combination inverter charger. One of them is power share, where if you know you're only plugged into a 15 amp outlet and you can tell it you're plugged into a 15 amp outlet, and then you turn on a lot of load downstream, well, then your charger could potentially cause you to trip that breaker that you're feeding your system with. But with a combination inverter charger, it can actually derate the charger while that heavy load is on. Then when the heavy load turns off, the charger comes back online. And you can only do that with a combination inverter charger. The other thing is knowing what causes electronics to age, whether you're talking about an inverter charger or a DVD player or anything that switches current using transistors or something like that. What causes them to age isn't a calendar year. They don't get old and spoil. What causes them to age is movement. You've got these transistors up against the heat sink, and as they heat up and as they cool down, they're constantly moving on this heat sink. And there are things like sill tape and things that we use to keep that motion from causing any problems. But eventually, the motion causes wear on the transistor. The transistor fails. Doesn't not to say that they're all going to fail, you know, in the next year, but thermal cycling causes electronics to age. If you are using your electronics when you're both plugged into shore power and when you're not plugged into shore power and you're using the same FETs and the same transistors and the same transformers, then that component is on all the time. When you have an inverter separate from your charger, then when you're unplugged, your inverter is heating up and working. And then when you plug in, the inverter cools down and the charger heats up and starts working. So just a couple of things that really make the combination inverter charger better for most installations. The third category I'm going to put in here is your workhorse inverter. So the first two I'm showing here are high frequency inverters. They tend to be very light, but where they're weak is that they don't surge very well. They typically surge twice the rated current for a few seconds, which is good enough for most applications. The Freedom SW is kind of a different category. It's a low frequency inverter. It uses a very large transformer. They're bigger, they're heavier, but they tend to surge very well. The Freedom SW inverter will surge 3 times its rated current and twice its rated current for minutes rather than seconds. Also, there's typically a lot more features in your larger low frequency inverters, like stackability. If you want to take 2 inverters and stack them together so it acts like a single larger inverter, or even to produce 240 volts or things like that. Networkability and that. Okay, so enough about inverters. Let's talk about the next line back, and that's batteries. So all kinds of batteries on the market, and we're going to drill really deep into batteries later on in the presentation. We kind of see batteries in these 2 different categories. One is the simple battery. Ours is 125 amp hours. It has an internal BMS. BMSs are important because the BMS is what protects the battery against things that would cause the battery to fail. You know, when you look at battery systems, especially lithium battery systems that fail, it's rarely the cells that fail. It's the BMS that was there to protect the battery that doesn't do its job. The second category we have are the external BMS batteries, where you can start stacking multiple battery cells and use a single BMS. So you can kind of grow and shrink the system as you need. One of the things that I feel is important, and there's a couple of us manufacturers that are doing this, and that is when you're talking about lithium batteries don't act like lead batteries. And again, we'll get into this in further detail later on, but lithium batteries, when they discharge and they get to a certain point, they shut completely off instead of brown out and get lower and lower and lower voltages. But they also turn off when there's a problem that the BMS needs to protect the battery from: high temperature, cold temperature, over discharge, overcharge, you know, things like that. So batteries tend to turn off. Well, when you're looking at a typical battery and it's just a brick on in the engine compartment and it turned off and you have no idea why. So one of the features that I've liked that we're starting to see more and more is Bluetooth connectivity to the battery, or some kind of connectivity to the battery. So you can take a display or your mobile device and connect to the battery and see what it's doing. If it's not working, you can scratch your head, or you can look at the battery's information, what it's telling you, and that makes troubleshooting go a lot faster. All right, so like I said, we're going to get into that deeper later on. Let's talk about solar controllers. I actually get asked about solar controllers an awful lot, specifically the difference between pulse width modulated and MPPTs. So PWMs are the older technology. They work fine. MPPTs came out a little later on. They typically are a little more expensive. But they're much more efficient, fewer losses in the inverters. So pulse width modulated controllers, they'll take in voltage, which is typically higher than the battery can take. Let's say the solar panel is putting out 19 volts. You can't tie that 19 volts to the battery. So what the pulse width modulated ones do is they literally turn that input on and off at a duty cycle that makes sure that the output averages the voltage you really want, your 14 volts to charge. But that means that controller is turning off the power generation from the solar panel, you know, let's say 30% of the time, which means you're losing 30% of your energy just by going through the controller. You're protecting the battery, you have to do it, but that there's energy on the table that we're not taking because we're using a pulse width modulated controller. They're less expensive. There's not really a lot wrong with that if you've got the solar panels and you can take that loss of energy and still build a system that works. You know, that's great. The MPPT controllers, however, what they do, there's a couple of benefits. First, they can take a much higher voltage in, where the pulse width modulated ones, your input voltage is going to be somewhat close to your battery voltage, so that you can chop that up. The MPPT, though, you can take 100 volts, you know, 78 volts or 60 volts or whatever, and it's going to take it. That means you can run your solar panels in series instead of parallel, which allows you to run a smaller cable from your solar panels to the controller, because you're bringing it in at higher voltage, lower amperage. Bring it to the controller will take it, and then what the controller does is it starts to draw power until it sees the solar panel voltage start to falter, and it calculates that as its maximum power point. So MPPT stands for maximum power point tracking, and once it finds its maximum power point, it pulls the energy from the panels at that voltage, chops it up, puts it through a DC to DC converter, outputs the proper voltage for the battery. And now, instead of losing 30% of your energy through a pulse width modulated controller, you lose about 7 to 9% of your energy. So it's much more efficient. If you've got a system that has panels, has a PWM controller, and you need to get some more energy out of it, well, you can add another solar panel, or you can simply upgrade to an MPPT controller, change the way the panels are connected together, put them in series instead of parallel, and just by doing that, you can eke out some more wattage to your batteries. Okay, so let's go back to panels. Panels are all over the place, different styles, different sizes, different wattages, efficiency factors, temperature factors, and all that. But they typically come in three different categories. You've got your standard glass panels, which are your rigid aluminum framed panels. You get your semi-flex panels, which have some flexibility to them. You can get some curve on not so flat surface. Like ours, you can see here that there's grommets. You can tie them down. And then the third is the super flexible panels, where you can actually get some really tight radiuses in them. And our company has a sprinter van that we use, and we ran some of these super flex panels down over the forehead of the high top, just to show that we could do it. It changes the angle of the sun, but it still can pull some energy in and feed the batteries. But there's a couple of key words that when you look at panels, the monocrystalline versus the polycrystalline. Polycrystalline is basically chopped up crystals. It's if you think about the difference between poly and mono, it's like the difference between OSB and plywood. Polycrystalline would be like OSB. You're taking these chunks of silicone and layering them together, pressing them into a wafer, and you can produce power from that. The monocrystalline they grow the wafer, or they grow the crystal larger, and then they slice the crystal, so it's a single color, it's a single piece. You can always tell the difference because the monocrystallines are very black, where the polycrystallines have that kind of iridescent layered look. But the monos tend to produce more energy per square inch than the poly, so they're a little bit better. The second technology you'll hear about is PERC cells, P-E-R-C. I should have put it on the screen, but I didn't. PERC cells, if you think about solar panels, they grab this light energy, but a lot of that light energy reflects off and goes away. So we can't quite get all of the energy that the sun wants to put out. We grab what we can. PERC cells, the best way to think about it, if you haven't kind of looked into the layered technology and how it works, but the best way to think about a PERC cell is think about a mirror being on the bottom of that cell. The cell will grab as much energy as it can, and then that light will bounce off of the mirror, and then the cell gets a second shot at trying to grab some energy off of that. You typically gain a few percentage points on efficiency with the PERC cells. So those are the technologies that folks are talking about that are somewhat emerging. Look for the monocrystalline and the PERC cells, and you'll get more energy per square inch. Okay, so we've looked at that, and then we'll get to the thing I get asked most about, and that's batteries. I spend more time talking about batteries and battery technologies than probably anything else. So let's look at batteries. Historically, we had our flooded batteries, our gel batteries, and our AGM batteries. These are lead-based batteries. They're big, they're heavy. The benefit of gel was that they were maintenance free. You could mount them in on their sides and things like that. So gels kind of took off. And then AGMs came into the scene, kind of pushed gels out of the way. AGMs were fairly expensive in the beginning. Now they're not quite as much when you compare them to flooded as they were, say, 20 years ago. But AGMs kind of took over the gel. Gels had a particular weakness in that you couldn't charge them as aggressively as a flooded battery, but an AGM you can. And so the AGMs have the benefit of the flooded batteries. They also have the benefit of the gel batteries, and they're sealed. You can mount them in different ways, and they don't gas. There's no maintenance. And then came the lithium batteries. Now, lithium batteries have been coming really fast. The different technologies are coming, and there's a lot of confusion and a lot of questions being generated about lithium technologies and the differences between them. So I'm gonna take a little bit of time on this, and I'll try to keep it unbiased. In fact, I'm going to show you some spider graphs. Now, these spider graphs come from batteryuniversity.com. It's not me. It's a website that validates battery technologies and gives you all kinds of information about it. If you have questions about batteries, any battery out there, batteryuniversity.com is a great source. But lithium cobalt are the first. I want to go back on this last bullet point. So the bottom, you'll see a few different chemistries. You've got the lithium cobalt oxide, the lithium iron phosphates, the nickel cobalt chemistries, and then there's a few others. But the top three are the ones we typically see. So what I'm going to do is I'm going to compare those top three using these spider graphs from batteryuniversity.com. Lithium cobalt is typically used where size and weight is the most critical feature you want. You think about handheld electronics, you think about electric cars, the airline industry, drones, things like that, where you really need small, lightweight energy storage. They have a much better power to weight ratio. The problem is they're way more volatile than lithium iron phosphates. When you look at the fires you see with the Samsung Note 7 and Tesla and even Boeing, these things all came from lithium cobalt chemistry batteries. Where they really shine is in their specific energy. So I wanted to, on the spider graph, the one thing that gets people confused is specific energy as opposed to specific power. Specific energy is how much energy you can store in a certain amount of volume. Specific power is the ability to dump that energy very quickly. So lithium cobalts don't do that very well. The other thing about cobalt is it's a heavy metal and needs to be disposed of properly. You just can't throw it in a landfill. That's bad. So let's look at the nickel manganese cobalt oxides. They do a little bit better than the lithium cobalt oxides. Their specific power is a little bit better. Safety is a little bit better. Performance is about the same. Lifespan is about the same. The cost is about the same. But again, we're still dealing with heavy metals because of the cobalt in them. Lithium iron phosphates are the chemistry that is safer. The downside of lithium iron phosphate is the specific energy portion of it. They are a little bit bigger. They are a little bit heavier than a lithium cobalt or any of the lithium cobalt variants, but they're way less volatile, and all the materials in them can be stripped and recycled and even put in the landfill. So when if you want to compare the three, take a quick shot of that. And again, if you want more information, batteryuniversity.com, it's a great resource for getting into those. Let's talk about lithium iron phosphates specifically. We talked about the cobalts. We talked about how they can be recycled. Also voltage stability through their entire cycle. Now that's in comparison to lead batteries. We'll get into that a little bit too. So they maintain a higher static voltage. The other thing is they can be left at 100% state of charge for longer than cobalt-based batteries. Anybody who has a drone or a Tesla or anything that uses the lithium cobalt batteries, if you're going to store them for a long period of time, you really need to discharge them to 50 to 70% state of charge before you store them, because if they sit at full voltage, their lifespan will suffer. They'll actually start to degrade over time. And so when you store them, you have to discharge them. For handheld electronics, it's not that big a deal because you charge every day, you discharge every day. Cars, you charge them every day, you discharge them every day. But one thing you don't want to do with your phones or your cars or anything that uses cobalt technology is leave them at full charge constantly. We saw a lot of cell phones damaging their battery over time because they were using these piggyback batteries and leaving the batteries on all the time. So the little battery pack was discharging every day, but the cell phone was staying at full charge every day, and the batteries would start to fail in the cell phones. Cathode's not as flammable as cobalt, and they age. Also, there's note at the bottom. Read about the Nissan Leaf and their struggles that they've been having, and even Tesla is announcing their move to lithium iron phosphates. Combustibility, we don't need to get too far into this. It's it's a dangerous chemical reaction that happens when cobalt burns. And you know, even lithium iron phosphate will burn, but not near to they're not near as dramatic, let's say, as a lithium cobalt battery. Last thing I want to talk about on the battery technologies is the UL standards. So UL 1973 has been a standard for lithium batteries. UL 2054 has been a standard for lithium batteries. UL 1973 was developed with the rail industry in mind. It's since been adopted for vehicle storage in a mobile environment. It has some specific tests that are important for vehicles that are in motion, even though the battery is not in motion like a handheld device. Crush testing, drop testing, vibration testing that are very, very strict. UL 2054 is a standard for a smaller battery bank. Intended UL 2054 to be the standard for handheld consumer electronics back when handheld consumer electronics were the only market for lithium batteries. They also say that it's not intended to be larger than 100 amp hours. So when you look at batteries that are listed UL 2054, and we want to stack a bunch of batteries together to get a very large battery bank, you want to be careful with that. And then just for the sake of being complete, UL 1642 is another standard, doesn't really apply to our market. It's more for small batteries like your rechargeable tools. So let's talk about the benefits of lithium batteries. One of the things I always get is, well, lithium batteries are more expensive than lead batteries. And I'm here to tell you that they're not. And let me explain that here. So we've got a 600 amp hour battery on the bottom. If we're going to build that battery bank in lead, a common way to do that is to use 6-volt batteries timed in series, 3 220 amp hours batteries, which gives us about 660 amp hours. It's a little bit more. And if we compare these two battery banks, one's 380 pounds, the other one's 165. One takes 2.82 cubic feet of volume. The other one takes 2.25 cubic feet of volume. And so when we look at this, there's not really a lot of difference, but it's not really a fair comparison when you compare amp hours to amp hours. The reason is because lithium batteries can discharge much lower than lead batteries. Lead batteries, we all know that batteries shouldn't be discharged below 50% state of charge, and all boaters know and follow this rule religiously. They never discharge their batteries below 50%, of course. And so when you do that, your batteries age. And so you really want to keep it up in that upper 50%, which means that 660 amp hour battery bank is 330 usable amp hours. Now, when on my lithium side, you'll see that I've got a little bit of blue at the bottom. That's because one of the features in our battery is that they'll discharge until they get to about 10%, and then they'll shut off. But they give you that added 10% reserve so that you can go and you can turn it on and you can use that energy to start a generator or do some things to get your charging going back up. But we give you that little reserve capacity at the end. But really, you could use almost the entire battery bank. But because you can use almost twice the amount of battery in a lithium battery than you can in a lead, the better comparison is against 12 of these 6-volt batteries, series parallel, 6 of these 12-volt lead modules. Now our weight and size difference is extreme. We're going 760 pounds compared to 165, and we're going to over 5.5 cubic feet compared to 2.25. And so that lead battery bank is pretty expensive. Well, so is the lithium battery bank, and the cost to install that battery bank is still higher on the lithium side. But I'm here to tell you that lithium is still cheaper, because when you talk about cycle life, lead batteries, the average lifespan of a lead battery in the marine market is about 800 cycles. Now, if you really take care of your batteries, you can probably get around 1,000 cycles. In some other markets, we see it closer to 500 cycles. But if I give the lead batteries the benefit of the doubt and say that we're gonna really take care of these batteries, we're gonna get that 1,000 cycles out of them. Well, a lithium battery can go better than 5,000 cycles, and in some cases, pretty close to 6,000 cycles. So even though that lithium battery is more expensive than that lead battery, it will outlast 5 banks of those lead batteries. And now when you look at it, when you look at actual cost of ownership, lithium actually has a much lower cost of ownership than lead. The other real benefit of lithium batteries, and as an electrical engineer, this is the part I appreciate the most, and that is its voltage stability. We talked about voltage stability earlier. When you look at a lead acid battery draining, a fully charged, a flooded battery is typically 12.65 volts, but at dead it's about 10.5, and so you have this constant slope down as the battery discharges and discharges and discharges. And I will call out that yes, the graph is wrong, because really we should be hitting 10.5 volts at the 50%, but I wanted to make it look a little better. Lithium batteries, as they discharge, their voltage is fairly stable until it gets to around that 10% state of charge. Then it starts getting into the 12 volt range, and at 12.1 volts, the thing's totally dead. Well, what does that do for us? Well, when you think about DC devices, especially motors, fan motors, pumps, and things like that, the lower the voltage that you're feeding it, the harder they have to work and the hotter they get. And heat causes things to age. So even though your lithium, we talked about the lithium battery will last longer than lead battery, the other thing you're going to see is devices last longer because you don't work them as hard. You're constantly keeping them above that 12 volt threshold that they were designed to work under, and not undervolting them most of the time that you're using them. So that for me is a huge benefit. Now, this brings us to the end. I did pretty good on time, I think. If you have any questions, Joe McCartney, he's our account manager for the marine market. He's kind of my bouncer. If you have questions, go through him, and he'll get me involved as needed. He's a smart fellow in his own right, though. Also, if you have just customer service questions, end user questions, things like that, customer service is always there via email or phone. Also, anything we publish, whether it's a user's manual, owner's manual, data sheets, or anything, is easily downloaded from our website. If you just go to xantrex.com, pick the device, or pick the inverter or solar panel or whatever, on the right you'll see data sheets and white papers and things like that. And if you can't find it there, we do have a document download section which covers all of the categories as needed. And I think here is where we end and open it up for questions.
Yeah, thanks again, Dom. Really appreciate it. I learned some good stuff there, and we do have some questions coming in. So once again, if you have any questions, you should see a little question box on your screen there. Type them in. We're not taking the hand raising like we do in our classes. There's too many people watching. So please type the question. We'll answer them if we can get to them. So the first question is, should long-range cruisers carry a spare external BMS for lithium iron phosphate batteries?
A spare external BMS? Probably not. I think, the BMS is an electronic device subject to failure. I'm kind of being careful saying that because I can't think of a single BMS that I've ever seen actually fail. In fact, to date, as long as we've been selling these batteries, I've only ever seen one battery fail, and it was just the worst thing that could happen. The guy pulled the battery out, left the BMS in the installation, and then bypassed the BMS and tried to charge it with something that wasn't a lithium charger, and the battery did some dramatic things. But so yeah, I wouldn't say keep a spare BMS any more than another spare electronic device, solar controller, things like that. Yeah, I would say no.
All right. Next question. With consideration of buying controllers, BMS, is lithium ion still cheaper than lead acid? Kind of
tying into what you were saying earlier.
Yeah, if you're going to own the system for a year, probably not. But if you're going to own it for 5, 7, 10 years, the longer you own it, the cheaper lithium will be in the long run.
Right. Next question is, please define BMS.
Oh, BMS, battery management system. Oh, I should have done that. So yeah, the lithium batteries themselves are just energy storage devices, but unlike a lead battery where you can just dump current into it and pull current out of it, and the lead kind of takes care of itself, you need a BMS to control the charge and control the discharge and protect the battery against external forces that would cause problems like cold weather. You really don't want to charge a battery under 32 degrees. Otherwise you get crystals that form and you'll start to degrade your cells. So the BMS will monitor battery temperature and disallow charging under 32 degrees, things like that. But it's a battery management system. It's the bouncer for the battery.
All right. Next question. What has been market experience with reliability of lithium battery systems? Consider batteries and the BMS.
I'll tell you, I've like I said, I've not seen a single battery go bad, and there have been lithium battery manufacturers before we got into lithium batteries, and even with that, I don't see a lot of failure outside of abuse, like the one example I gave. Yeah, I've got stories of all kinds of different things happening, going wrong with different devices and our products, our competitors' products. But you'd see a lot of lead batteries, especially if when times are good and the economy is doing great and battery manufacturers are trying to get batteries out the door very quickly. Sometimes they won't fully form the battery at the factory, and they'll send them out partially formed. With the intent that you're going to put them in and start to charge them immediately, to charge them to full and hold them on a charger, which completes the forming process. But if instead you install the batteries and you discharge them immediately, then those batteries never really form well, and they won't perform. And so, yeah, I see way more battery issues with lead batteries than I do lithium batteries.
Right. Next question. Do you suggest having a controller for every solar panel for the most efficiency?
Well, it depends on what electrical efficiency that it's there. Efficiency to my bank account, I wouldn't think so. No, I think if you're really looking to eke out as much efficiency as you want, the best installation I've seen is, especially if you think about a sailboat where you've got solar panels on the left, solar panels on the right. Run the solar panels in series, put them through an MPPT, run the other side, a bunch of solar panels in series, give it its own controller, so that when your sail shades one side, you're not getting that negative effect on the other side as well. You'll still get a little bit off of that one string. But no, I wouldn't put a controller for each panel. That's a little bit of redundancy that you don't need.
All right. What is needed for alternators to match charging requirements of lithium-ion batteries?
Oh, well, a regulator that's configured for lithium. So we've got a couple of strategies that we use for charging lithiums off of alternators. The first is obviously the regulator. The alternator regulator needs to have a lithium setting. In some of our installations, we actually eke out a little bit of extra current from the engines using the engine's alternators. But the engine alternators were not designed to charge a lithium battery. And so we have a little solenoid controller. Basically, it's just a standard, you use whatever combiner solenoid you normally use. But this controller works kind of like the your battery combiner circuits, but it's also intended to protect the lithium side of the battery. So instead of connecting when the engines are running and letting all that charge go to the lithium battery and then leaving it connected, it'll connect, allow that current to go to the lithium battery, and then when the lithium battery gets up in its state of charge, it'll then disconnect before the battery gets to full charge, so we don't expose that that lithium battery to voltages that it might not like and cause the BMS to protect it. So there's a couple of different strategies you can use, but the number one is if you're using a standalone alternator that's additional to the engine's alternator, just make sure you've got a lithium rated regulator on it.
All right. How would you go about sizing a battery bank end system for quite irregular usage patterns?
Assume the worst. So irregularity is the thing. Like I said earlier, if you do all the math and it works 90% of the time very well, that last 10% is going to frustrate you. So either oversize the solar so you have the potential to harvest more than you need on your normal days, oversize your battery so that you have that deep cycle capability on your off days, or carry a third source of power like a generator or something like that, or even like an alternator on an engine with some kind of combiner circuit, so that you can use your generator or your engines as a DC generator. But that's what I tell people all the time: oversize. And that's not me trying to sell more solar panels. It's just, you don't want that 10% to get you in trouble.
All right. What is the most common cause of premature failure with lithium batteries?
Cold. Well, so cold storage. If you leave them in sub freezing temperatures for long periods of time, if you or even hot temperatures for that matter, you really want to keep the batteries temperature. In fact, one of the things I tell some of my markets, my customers, is that if you can put the lithium battery inside the cabin, you're better off than putting it in outside in the engine room or something like that, because if you're comfortable, the battery's going to be comfortable. Yeah, I mean, really, it's just about abuse. Read the warning labels in the manuals, and try to stay within those warnings. Again, the BMS will protect the battery as best it can, but the big thing that causes a battery to not last that 5,500 cycles or 5,000 cycles is keeping it in a bad environment for a long period of time.
All right. Is there a product that can communicate with your BMS to monitor your phone or monitor your battery bank using your cell phone that you know of?
Yeah, so I was saying that both categories of our batteries actually have a Bluetooth antenna in them, and we have a battery app. If you search Google Play or the Apple Store, just type in Xantrex Battery and you'll see the battery app. And then just opening up the app, it will find the right Bluetooth signal it's looking for. It'll say, hey, I've got a battery nearby. You can connect to the battery, and its matrix it gives you all the different parameters it's looking for. So there's this, I should have had a screenshot on this. There's a matrix of different categories, like high temperature, low temperature, low state of charge, reserve capacity. Like if it goes into that 10% reserve capacity, there's a spot for that. And you open it up, and it'll tell, and the red ones are the ones to pay attention to. So if it's in reserve capacity, then that reserve capacity square goes red. If the battery's in a fault state, the battery information screen will go red. But it also gives you amperage, discharge, voltage, percentage, state of charge, things like that. So it's pretty neat.
All right. How close is the industry towards integrating supercapacitors?
Probably not. I think supercapacitor technology is it hit its stride. I don't think there's going to be a lot of new up-to-date manufacturing processes or anything like that that's going to bring the cost of supercapacitors down. There are some other kind of emerging battery technologies that we might see some real benefit in 10-ish years. But I think for the foreseeable future, lithium is going to be the big thing. The other thing about supercapacitors is Supercapacitors and lithiums are kind of their own nemesis in that they're meant for different usages. Supercapacitors are for starting engines typically. Very fast amperage dump is where a supercapacitor really comes into play while maintaining good voltage. So you want to start an engine, you will not get that slow cranking with a lead battery if you're using a supercapacitor. Lithium is meant primarily for deep storage. In fact, you look at a typical group 31 battery, a lead battery, I can start my engine because a lead battery can dump 400 amps very quickly. But a group 31 lithium battery typically is limited to 100 amps. And so you can't start engines with a lithium battery unless you really stack these batteries up and get them up. But again, that's not their strong suit. Their strong suit is really in deep cycle. So yeah, I don't think the supercapacitors and lithium batteries will ever compete with each other, but I am waiting for the day that the lead engine starting batteries go away to something affordable like a supercapacitor, but I don't see that coming yet.
All right, I think we got time for one more quick question here. It's a good one. If a battery or a lithium ion battery is on fire, how do you extinguish it?
You can't. The only thing you can do is protect what's around it, and that's really where, like I said, the Samsung Note 7 and even Boeing, that's really the biggest concern is how do you protect what's around it. But once lithium ignites, it's going to burn out. So one of the things in our big battery, I showed you the small battery in our big battery. One of the things in our big battery that we're very proud of is each of our cells has a protective curtain around it, that if that cell goes into thermal runaway, the curtain goes through a chemical change and creates a protective shell around that burning battery. In fact, one of the tests we do that we've got some video of that's pretty cool is we take a pneumatic air gun, nail gun, and we pop a nail in the side of our battery, and we watch a little puff of smoke, and that cell starts to go into thermal runaway like it's going to do when you do that. These are in some of our old plastic cases. Now we're in metal cases, so the nail guns don't work as well. But then it stops. You can kind of hear some stuff going on, but what's happening is that curtain is protecting that cell because we can't stop that cell. But what we can do is stop it from spreading to the cells on either side of it, or worse, spreading outside of the case. So yeah, once a lithium battery starts, it's really about protecting what's around it.
All right, that puts us almost to our stop time here. Don, I really appreciate it. I'm going to jump back on camera to close it out here.
Okay.
Thank you, everyone, again, for participating here. We love doing these things. Don was kind enough to offer some contact there. I've been told that the correct phone number is 1-800-670-0707. So
typo on my part. Sorry about that.
That's okay. So once again, thank you, Don. Thank you to the team over at Xantrex. We really appreciate you participating in this. I put out the dates for the upcoming ones. If you're watching this on YouTube, you'll see the link pop up somewhere on the screen here. Matt always puts it somewhere else. So you'll see the link pop up to apply for CEUs. Everyone else should be getting an email, follow-up email tomorrow around noon, which will have that link for you. So without further ado, thank you very much, Don. Once again, we really appreciate it. And everyone stay safe, and we will see you in October.
Thanks for having me.
All right, take care.